Picture this: 95% of the universe is missing, not hiding, not overlooked, but utterly invisible to everything we've ever built to see it. The stars, the galaxies, the cosmic web stretching across the void, everything we call the universe, is just the glittering tip of an iceberg floating in an ocean of shadows. And the deeper we look, the more unsettling the truth becomes. Dark matter and dark energy, the twin phantoms haunting modern physics, aren't just gaps in our knowledge. They're proof that reality as we know it is built on foundations we don't understand. Think about that for a moment. Every telescope, every experiment, every equation humanity has ever crafted to decode the cosmos has only illuminated 5% of existence. The rest, a mystery so vast it rewrites the rules of time, space, and gravity itself. Dark matter's invisible grip holds galaxies together, while dark energy, whatever it is, pushes the universe apart faster than light should allow. These aren't just scientific curiosities, they're cosmic paradoxes that defy everything we thought we knew, and the wildest part, the more we learn, the stranger the questions get. That's where this journey begins. Over the next 30 mysteries, we'll unravel the enigmas that keep physicists awake at night. From ghostly particles that pass through you by the billions every second, to the chilling possibility that our universe is just one bubble in an infinite cosmic foam. This isn't just about distant stars or abstract math, it's about the very fabric of reality and our place within it. So if you've ever stared up at the night sky and felt that tug of wonder, that itch to know what's really out there, you're about to dive deeper than ever before. The universe is stranger than we imagined, and the best part, we're just getting started. Here's the strangest thing about dark matter: it doesn't just hide from our eyes. It ignores light entirely. Picture a cosmic game of hide and seek where one player doesn't just duck behind a tree, but refuses to interact with the seekers in any way. That's dark matter. It doesn't absorb, reflect, or emit light, not even a flicker. And yet, we know it's there because the universe would tear itself apart without it. Take galaxy rotation, for example. Stars orbiting the center of a galaxy should slow down the farther they are from the core, just like planets in our solar system move more sluggishly the farther they are from the sun. But they don't. Stars on the outer edges of galaxies whip around just as fast as those near the middle. The only way this makes sense, an invisible mass, dark matter, must be holding them in place with its gravitational pull. It's like watching a carousel spin at full speed while half the horses are missing. We can't see them, but something's keeping the ride from flying apart. Then there's gravitational lensing, where massive objects bend light around them like a cosmic magnifying glass. When astronomers study distant galaxies, they often see their light warped in ways that suggest far more mass is present than what's visible. Again, dark matter steps in as the unseen architect, shaping the universe in ways ordinary matter never could. So why hasn't science caught this elusive phantom yet? The problem isn't just that dark matter doesn't interact with light. It barely interacts with anything. Billions of dark matter particles might be passing through you right now, leaving no trace. That's what makes it so maddening. We're surrounded by the stuff, wrapped in its gravitational embrace, yet it slips through our detectors like smoke through a sieve. Some theories suggest dark matter could be made of exotic particles. We've yet to discover entities that don't fit the rules of the standard model. Others wonder if we're missing something fundamental about gravity itself. Either way, one thing's clear: dark matter isn't just a puzzle. It's a glaring sign that our understanding of the universe is still, in many ways, just scratching the surface. If dark matter truly sculpts the universe, then where are all the missing galaxies? Computer simulations paint a startling picture. When scientists model how dark matter should clump together under gravity, their cosmic blueprints predict thousands of tiny dwarf galaxies orbiting giants like the Milky Way. But when we point our telescopes at the sky, only a few dozen appear. This glaring mismatch, known as the missing satellite problem, isn't just a counting error. It's a crisis for our understanding of how dark matter shapes the cosmos. Imagine building a jigsaw puzzle where most pieces refuse to fit. That's what physicists face. Supercomputer simulations like the famous Via Lactea and Aquarius projects track virtual dark matter particles over billions of cosmic years. Every time they produce elaborate halos, vast, invisible clouds surrounding galaxies, with countless dense knots where gravity should have compressed matter into dwarf galaxies. Yet scans of our galactic neighborhood reveal barely a fraction of these expected satellites. The implications rattle astrophysics to its core. Maybe dark matter isn't as sticky as we thought. Some theories suggest it might interact weakly with itself, preventing those dense knots from forming stars and becoming visible. Others propose that early radiation from the first stars blasted away gas needed to build these dwarfs, leaving them dark and nearly undetectable. Or perhaps we're searching wrong recent discoveries of ultra-faint galaxies, so dim they blend into the cosmic background, hint that our inventory might still be incomplete. Then there's the most radical possibility. What if dark matter isn't cold and slow-moving as most models assume? Warm dark matter particles zipping through space at higher speeds could smear out those dense clumps, explaining the shortage. It's a cosmic detective story where every clue leads to deeper questions. The real shock, this isn't just about missing galaxies. It's about realizing that dark matter might play by rules we haven't even written yet. As telescopes grow sharper and simulations more refined, each answer only peels back another layer of the mystery. The universe, it seems, enjoys keeping its secrets. One of the most compelling pieces of evidence for dark matter's existence comes from a cosmic car crash over 3 billion light-years away. The Bullet Cluster, a pair of colliding galaxy clusters, reveals something extraordinary. When these titanic structures slammed into each other, something unexpected happened. The visible matter, the hot gas glowing with X-rays, got stuck in the middle like two clouds of smoke merging. But the dark matter, it kept right on going, slipping past the collision as if it weren't even there. This cosmic sleight of hand wasn't just a fluke. It was proof that dark matter doesn't play by the same rules as everything else in the universe. Think of it like a ghost walking through a crowded room. The people representing normal matter bump into each other, slowing down as they interact, but the ghost, it glides straight through, untouched. That's exactly what we see in the Bullet Cluster. The dark matter components of these clusters, detected through their gravitational lensing effects, sailed past the wreckage of the collision completely unimpeded. If dark matter interacted like normal matter, it would have pooled in the center with the hot gas. Instead, it behaved like an invisible spectator, indifferent to the chaos unfolding around it. This separation between dark and visible matter isn't just a curiosity, it's a major clue. It tells us dark matter doesn't just ignore light, it barely interacts with anything at all. No collisions, no friction, no electromagnetic forces. The only way it makes its presence known is through gravity. That's why the Bullet Cluster is such a landmark discovery. It didn't just confirm dark matter exists, it showed us how fundamentally different it is from everything we've ever seen. Yet, for all it reveals, the Bullet Cluster also deepens the mystery. Why doesn't dark matter interact with itself? If it's made of particles, shouldn't they occasionally bump into one another? Some experiments have searched for signs of even the faintest interactions, like the possibility that dark matter particles might scatter off each other in subtle ways, but so far, nothing. The more we study cosmic collisions like this one, the more it seems dark matter is even more aloof than we thought, and that raises an even bigger question. If dark matter refuses to interact with anything except gravity, how do we ever hope to detect it directly? Underground labs around the world are hunting for rare flashes of energy that might signal a dark matter particle brushing against an atom. Space telescopes map its gravitational fingerprints across the universe, but the bullet cluster reminds us that dark matter might be playing an entirely different game, one we're only beginning to understand. Every breakthrough peels back another layer, revealing not just answers, but a universe far stranger than we ever imagined. The core cusp problem might sound like an obscure technical term, but it strikes at the heart of one of dark matter's most baffling contradictions. Here's the puzzle. Supercomputer simulations predict that dark matter should pile up in dense, sharp peaks at the centers of galaxies, what scientists call cusps. Yet when astronomers measure real galaxies, they find these cores are smoother and flatter than the simulations suggest. It's like expecting a mountain peak and instead finding a gently rolling hill. This mismatch isn't just a small error. It challenges our entire understanding of how dark matter behaves. Take dwarf galaxies, for instance. These small, faint galaxies are ideal laboratories for studying dark matter because they're dominated by it, with relatively little ordinary matter to muddy the signal. Simulations show dark matter in these galaxies should be densely concentrated at their cores, creating a steep gravitational well, but observations tell a different story. The dark matter in many dwarfs appears more evenly spread, as if some unseen force has been stirring it like syrup in a cup. This discrepancy has forced physicists to reconsider some fundamental assumptions. One possible explanation: dark matter might interact with itself in ways we haven't accounted for. The leading theory, cold dark matter, assumes these particles are cold, meaning they move slowly and barely interact except through gravity. But what if they occasionally bump into each other like billiard balls on a cosmic scale? This idea, called self-interacting dark matter, could explain why cores are smoother. Those gentle collisions would scatter particles outward, softening the dense cusps predicted by simulations. It's a subtle tweak, but it might solve the problem without throwing out our entire model. Then there's the role of ordinary matter, which isn't just a passive bystander. When stars form, they unleash torrents of energy, supernova explosions, stellar winds, and radiation that can push gas around like a cosmic leaf blower. This feedback might indirectly sculpt dark matter, stirring it up and smoothing out the central cusp. Think of it like dropping a rock into a pond. The ripples don't just affect the surface, they disturb everything beneath. If stars and supernovas act like those rocks, they could be reshaping dark matter in ways simulations are only starting to account for. But here's where things get even stranger. Some galaxies, like the ultra-diffuse Dragonfly 44, have almost no stars yet still show smooth dark matter cores. If stellar feedback isn't the culprit there, what is? This has led to even wilder ideas, like dark matter being fuzzy, made up of ultralight particles that behave more like waves than discrete clumps. Or perhaps our understanding of gravity itself needs revising. The core cusp problem isn't just about fixing a glitch in the simulations. It's a sign that dark matter might be more complex and more fascinating than we ever imagined. Every proposed solution opens new questions, turning what seemed like a small inconsistency into a window onto a deeper mystery. And that's the essence of dark matter research. Each answer peels back another layer, revealing just how much we have left to learn. The too big to fail problem sounds like a corporate drama, but it's actually one of dark matter's most stubborn puzzles. Picture this. Our Milky Way isn't floating alone in space. It's surrounded by satellite galaxies, smaller cosmic companions bound by gravity. According to dark matter simulations, the most massive of these satellites should be brimming with enough dark matter to form dazzling stars and robust structures. But when we look at real galaxies like Andromeda's companions or the Milky Way's own satellites, something's off. These galaxies are far dimmer and less massive than the simulations predict. It's as if the universe handed out tickets for a blockbuster party, only for most guests to show up underdressed and half asleep. Why does this matter? Because these Too big to fail galaxies, so named because their dark matter halos should have made them thriving cosmic hubs, are curiously feeble. Simulations like the renowned Eagle project generate virtual universes where these satellites shine brightly, packed with stars and gas. Yet reality paints a different picture. Take the Fornax dwarf galaxy, one of the Milky Way's largest satellites. It should be a bustling stellar metropolis, but instead, it's a sleepy town with barely any recent star formation. This mismatch isn't just a quirk, it's a direct challenge to our models of how dark matter shapes galaxy evolution. One leading theory points to tidal stripping, the cosmic equivalent of getting caught in a gravitational rip current. As satellites orbit their host galaxies, tidal forces might rip away their gas and dark matter, leaving them stunted. Imagine a tree losing its leaves in a storm. Over time, these galaxies could be stripped down to skeletal versions of themselves. But here's the catch: some satellites, like the ultra-faint Boötes I, are so tiny and dark matter-rich that tidal stripping can't fully explain their puny starlight. That's where alternative dark matter properties come in. What if dark matter isn't perfectly cold but slightly warm, with particles moving fast enough to resist clumping tightly? Warm dark matter would smear out the densest halos, preventing satellites from growing as massive as simulations predict. Or perhaps dark matter interacts with itself, creating friction that heats up these systems and stifles star formation. There's even a wild card. Feedback from supernova might have blown away the gas needed to fuel these galaxies, leaving them dark matter heavy but star-poor. But the plot thickens. Recent discoveries of quenched satellites galaxies that mysteriously stopped forming stars add another layer. If tidal stripping or supernova were the sole culprits, we'd expect a clearer pattern. Instead, the evidence is messy, suggesting multiple forces are at play. Some researchers argue we're missing a key piece of physics in our simulations, like the way dark matter responds to cosmic radiation in the early universe. Others wonder if these satellites are cosmic latecomers, arriving after their gas reservoirs were already depleted. The too big to fail problem isn't just about fixing a glitch, it's a window into dark matter's quirks. Every solution we test reveals new complexities, reminding us that the universe loves to defy expectations. Whether it's tidal forces, exotic particle physics, or something even stranger, one thing's clear: dark matter isn't just hiding from us. It's rewriting the rules as we go. Dwarf galaxies are the cosmic equivalent of snowflakes. No two seem to follow the same blueprint when it comes to dark matter. Some, like the ultra-diffuse Dragonfly 44, are practically invisible, with 99.9% of their mass hidden in dark matter. Others, like the star-heavy Large Magellanic Cloud, barely seem to need dark matter at all. This staggering diversity isn't just a curiosity, it's tearing at the seams of our understanding of how galaxies form. Take Segway 1, a tiny satellite of the Milky Way. This dwarf is so dominated by dark matter that astronomers estimate it contains 1,000 times more dark mass than visible stars. It's like finding a featherweight boxer who somehow punches with the force of a wrecking ball. Then there's NGC 1052DF2, a ghostly galaxy where dark matter appears to be missing entirely. Stars drift through it like ships without anchors, defying every expectation of how gravity should bind them together. These extremes shouldn't coexist under our current models, yet they do, side by side in the same cosmic neighborhood. So what's causing this wild variation? One clue lies in the chaotic environments these dwarfs endure. Picture a small boat caught between tidal forces. The gravitational pull of a massive host galaxy like the Milky Way can stretch and strip a dwarf, redistributing its dark matter in unpredictable ways. Some galaxies might lose their dark halos entirely, while others have theirs compressed into denser configurations, but tidal forces alone can't explain the full spectrum. For every tidally shredded dwarf, there's another like Triangulum 2, which clings to a shockingly dense dark matter core despite its proximity to the Milky Way's gravitational grip. Then there's the role of feedback, the cosmic balancing act between star formation and destruction. In some dwarfs, supernova explosions might have blown away loose dark matter, leaving behind a more concentrated core. Others could have had their dark matter heated up by repeated stellar outbursts, causing it to spread out more evenly. This would explain why star-forming dwarfs often show different dark matter profiles than their quiescent counterparts. But even this theory hits snags when faced with galaxies like Crater 2, which has almost no star formation yet possesses a bizarrely low dark matter density, as if something erased it entirely. The real headache for theorists, these discrepancies might hint at dark matter's fundamental nature. If dark matter particles can interact with themselves or with other forces beyond gravity, that could explain why they clump so differently from one galaxy to the next. Some models propose self-interacting dark matter that collides and scatters, smoothing out dense cusps in certain environments. Others suggest fuzzy, dark matter particles so lightweight they behave more like waves, creating diffuse halos in some galaxies and tight knots in others. Yet with every potential solution comes a new paradox. If dark matter is truly this malleable, why do some galaxies resist the trend? The answer might lie in the universe's toddler years. The conditions during the epoch of reionization, when the first stars flooded space with radiation, could have sterilized some dwarfs, preventing them from ever forming enough stars to alter their dark matter distributions. Others, born in quieter cosmic backwaters, might have preserved their original dark matter blueprints unchanged. What's clear is that dwarf galaxies aren't just smaller versions of their grand spiral cousins. They're a laboratory for dark matter's weirdest behaviors. Their diversity forces us to ask uncomfortable questions. Are we missing a crucial piece of galaxy formation physics? Could dark matter itself have multiple flavors or states? Every oddball dwarf we discover chips away at the illusion that we've got the cosmic rulebook figured out, and that's what makes them so thrilling. In their quiet, flickering light, we're catching glimpses of a universe far more nuanced than our theories ever predicted. Ultra-diffuse galaxies are the universe's greatest ghost stories, vast, sprawling cosmic structures that somehow exist without being seen. Take Dragonfly 44, a galaxy so faint it was missed by telescopes for decades. Yet when astronomers finally spotted it, they found something astonishing. This wispy, nearly invisible cloud of stars isn't just big, it's roughly the same size as the Milky Way. But here's the catch, it emits less than 1% of our galaxy's light. The reason? 99.9% of its mass is hidden in the form of dark matter, an unimaginable halo of invisible material holding this spectral giant together. This discovery shattered expectations. Normally, a galaxy this massive should blaze with the light of billions of stars, but Dragonfly 44 is more like a cosmic mirage, a shadow of what a galaxy should be. Even stranger, it's not alone. Surveys have uncovered entire populations of these ultra-diffuse galaxies, each floating through space like ethereal islands. Some, like NGC 1052DF2, take the mystery further by appearing to lack dark matter entirely, their stars drifting in defiance of gravitational logic. How can two galaxies of similar size and structure behave so differently? The answer might rewrite our understanding of dark matter itself. One theory suggests these faint giants are failed galaxy systems that started with all the right ingredients but never managed to ignite robust star formation. Picture a car engine turning over but never starting. Without enough stars, these galaxies remain dim, their dark matter halos lingering like unopened blueprints. But that doesn't explain why some, like Dragonfly 44, are so rich in dark matter while others seem to have misplaced it entirely. Another idea points to tidal stripping, the gravitational equivalent of being caught in a cosmic whirlpool. If an ultra-diffuse galaxy passed too close to a massive neighbor, it might have had its gas and stars torn away, leaving behind a dark matter skeleton. Yet this doesn't account for isolated examples floating in quiet stretches of space, far from disruptive forces. Then there's the radical possibility that dark matter isn't uniform. What if it comes in different flavors, some sticky and clumpy, others smooth and diffuse? This could explain why some galaxies hoard dark matter like dragons guarding treasure, while others let it slip through their fingers. Or perhaps our measurements are missing something like hidden streams of dark matter weaving between galaxies, invisible even to our most sensitive detectors. The existence of ultra-diffuse galaxies forces us to confront an uncomfortable truth. Dark matter might not play by a single set of rules. These ghostly giants are more than cosmic oddities. They're living proof that the universe still has secrets we've barely begun to uncover. Every time we think we've pinned down dark matter's behavior, another wisp of starlight whispers, "Think again." The Planck satellite didn't just map the cosmos, it took its temperature. For over 4 years, this European Space Agency mission scanned the sky with unprecedented precision, measuring the faint afterglow of the Big Bang, the cosmic microwave background. These ancient photons, traveling for over 13 billion years, carry imprints of the universe's infancy, and hidden within them clues to dark matter's secrets. What Planck revealed was both groundbreaking and deeply puzzling. By analyzing slight variations in the microwave background's temperature fluctuations as subtle as 1 part in 100,000, Planck painted a shockingly precise portrait of the universe's composition. 26.8% dark matter, 68.3% dark energy, ordinary matter, a mere 4.9%. These numbers are now etched into cosmology textbooks. But here's the catch. While Planck confirmed dark matter's gravitational influence with razor-sharp accuracy, it told us almost nothing about what dark matter actually is. It's like knowing the exact weight of an invisible object in your hand, but having no idea whether it's made of metal, glass, or something entirely unknown. The real intrigue lies in how Planck's data narrowed the possibilities. Certain dark matter candidates, like warm dark matter particles moving at near light speeds, would have left distinctive smudges on the cosmic microwave background. But Planck's pristine maps showed no such fingerprints, ruling out entire classes of theories. Similarly, the satellite's measurements of how matter clumped in the early universe disfavored models where dark matter interacts strongly with itself or with ordinary particles. The conclusion: dark matter must be cold, slow-moving, and extraordinarily aloof, a ghost that shapes the cosmos but refuses to leave fingerprints. Yet even as Planck tightened the constraints, it deepened the mystery. The satellite's data perfectly aligns with the simplest theoretical framework called collisionless dark matter, but that very simplicity is now causing headaches. Why? Because as we've seen with dwarf galaxies and galaxy clusters, real-world dark matter behaves in ways that sometimes contradict this neat model. Planck gave us a universe where dark matter's bulk properties are exquisitely measured, yet its microscopic nature remains maddeningly out of reach. Perhaps most tantalizing is what Planck didn't find. Some theorists hope the cosmic microwave background might reveal indirect signs of dark matter particles annihilating or decaying in the early universe, a faint signal buried in the radiation. But no such trace emerged. This absence isn't just a disappointment, it's a clue. It suggests dark matter might be even more inert than we imagined, not just ignoring light and matter but barely interacting with its own kind. So where does that leave us? With a paradox. Planck's measurements are the gold standard for cosmology, yet they've boxed dark matter into a corner where it's simultaneously everywhere and nowhere. We know how much there is. We see its gravitational handiwork across billions of years, but the closer we look, the more it feels like we're chasing a shadow, one that redefines itself every time we think we've grasped its edges. The universe, it seems, is still holding its cards close. For decades, physicists have been playing the ultimate game of hide and seek, searching for dark matter particles with detectors buried deep underground, shielded from cosmic interference. Laboratories like LUX, Xenon, and Panda X have scoured the darkness for signs of weakly interacting massive particles, or WIMP, the long-favored dark matter candidate. These experiments are marvels of engineering, ultra-sensitive vats of liquid xenon or argon, waiting for the faintest flash of light or ripple of charge that might betray a dark matter particle's passage. Yet year after year, the results have been the same: nothing, not a single definitive signal. The scale of this silence is staggering. Early theories suggested WIMP should be abundant enough to produce thousands of detectable collisions in these experiments. But as detectors grew more sensitive, capable of spotting interactions as rare as 1 per century per ton of material, the void only deepened. It's like listening for a whisper in a silent room, only to realize the speaker might not even be there. This relentless absence has forced physicists to confront an uncomfortable possibility. What if dark matter isn't just hiding? What if we've been searching for the wrong thing entirely? Some argue the experiments aren't failing, they're succeeding at ruling out possibilities. Each null result narrows the range of viable WIMP properties, like a cosmic game of 20 questions. Maybe dark matter particles are lighter than expected, slipping through detectors like neutrinos. Or perhaps they're heavier, with interactions so feeble they defy current technology. There's even the chance WIMP don't interact with ordinary matter through conventional forces at all, leaving our detectors blind to their presence. Yet alternative explanations are bubbling up. Axions, hypothetical particles billions of times lighter than electrons, have surged as a compelling candidate. Unlike WIMP, axions wouldn't leave tracks in xenon tanks. They'd reveal themselves by converting into photons in strong magnetic fields. Experiments like ADMS are now tuning their detectors like radios, scanning for axions' faint signatures. Others are exploring the idea of stealthy, dark matter, particles that interact only gravitationally or through exotic forces beyond the standard model. The most provocative possibility: dark matter might not be particulate at all. Some theorists suggest it could be primordial black holes, ancient relics from the Big Bang's first moments. Others propose it's a quantum field permeating space with fluctuations that mimic particle behavior. These ideas aren't just wild speculation, they're born from necessity as traditional searches keep hitting walls. What's clear is that the direct detection dilemma isn't just a technical challenge, it's a philosophical one. Every empty detector forces us to question whether we're asking the right questions. Dark matter's elusiveness might be the universe's way of telling us to think differently, to look beyond the frameworks we've clung to for decades, and that's where the real excitement lies. In the hunt for what we can't find, we might stumble upon something far stranger than we ever imagined. In the hunt for dark matter, physicists have had to think beyond the conventional, and that's where axions come in. Unlike the bulky WIMP that dominated early searches, axions are featherweight contenders, hypothetical particles so insubstantial they make electrons look like sumo wrestlers. Born from an elegant solution to a completely unrelated puzzle in particle physics, the mysterious symmetry of the strong nuclear force axions were never meant to be dark matter candidates. But here's the twist: if they exist, they could solve two cosmic riddles at once. Imagine a universe filled with an invisible, intangible mist, a quantum field that permeates every corner of space. Axions would emerge as tiny ripples in this field, barely interacting with ordinary matter but exerting just enough gravitational pull to explain dark matter's effects. Their theoretical appeal lies in their simplicity. Unlike WIMP, which require complex extensions to the standard model, axions fit neatly into existing frameworks. They're the cosmic equivalent of finding a missing puzzle piece you didn't realize was under the couch all along. But how do you catch something as elusive as an axion? Enter ADMX, the Action Dark Matter Experiment, a detector that operates more like a high-tech radio than a traditional particle collider. Hidden beneath the University of Washington, ADMX uses a powerful magnetic field to coax axions into revealing themselves. If these particles are out there, the magnetic field should convert them into faint microwave photons, a signal so quiet it's like listening for a single snowflake landing in a blizzard. The experiment tunes its receiver across millions of frequencies, searching for the telltale hum of axions converting into light. What makes axions so tantalizing is their versatility. Depending on their exact properties, they could explain not just dark matter, but also why neutron stars sometimes flicker in unexpected ways, or why certain quantum calculations defy expectations. Some theories even suggest axions might form exotic, galaxy-spanning structures like Bose-Einstein condensates where trillions of particles behave as a single quantum wave. It's a dizzying possibility. Dark matter might not just be invisible matter but an entirely new state of it. Yet the axion hypothesis isn't without its skeptics. If these particles are so light, why hasn't the universe's natural particle accelerator, the Big Bang's afterglow, produced them in detectable quantities? Others argue that axions might be too cold, failing to explain the odd distributions of dark matter in some galaxies. But ADMX isn't flying blind. Recent upgrades have pushed its sensitivity into uncharted territory, and collaborations like CAP in South Korea and Haystack in the US are joining the hunt with novel techniques. The beauty of the axion quest lies in its audacity. It's a reminder that sometimes the most profound answers come from reimagining the questions. Whether axions are the key to dark matter or just another stepping stone, their pursuit is reshaping our understanding of the universe's hidden architecture, one whisper at a time. Neutrinos are already the universe's most elusive known particles. Billions pass through your body undetected every second, barely interacting with anything at all. But what if there's a shadowy cousin to these ghostly particles, one even more aloof? Enter sterile neutrinos, a hypothetical heavyweight variant that could solve two cosmic puzzles at once: dark matter's identity and the strange behavior of ordinary neutrinos. Unlike the three neutrino flavors we've detected, electron, muon, and tau sterile neutrinos would interact only through gravity, making them nearly invisible to our detectors. Yet their gravitational footprint might be exactly what's holding galaxies together. The case for sterile neutrinos starts with an anomaly. Ordinary neutrinos have a bizarre habit of shape-shifting as they travel, oscillating between flavors in ways that initially baffled physicists. But certain measurements, like those from the LSND and Mini-Bueni experiments, detected more oscillations than the standard model can explain. It's as if there's a hidden fourth neutrino flavor, one that doesn't respond to the weak nuclear force, hence sterile. If these particles exist, they'd be far heavier than regular neutrinos, potentially forming the scaffolding of dark matter halos while their lighter cousins zip through space unimpeded. Yet the plot thickens when we ask how sterile neutrinos could have been forged in the early universe. The Big Bang's fiery chaos should have produced them in vast numbers, but calculations suggest they'd either overproduce or underproduce the dark matter we observe today. Some models propose a delicate balancing act, sterile neutrinos decaying just enough to leave behind the right abundance, like a cosmic Goldilocks scenario. Others argue they might have been spawned not by the Big Bang's heat but by collapsing stars or quantum fluctuations in primordial plasma. The real headache comes from X-ray observations. If sterile neutrinos decay, they should emit faint X-ray signals at specific energies. A tantalizing line spotted near 3.5 kilo-electron volts in galaxy clusters like Perseus sparked excitement, but follow-up studies failed to confirm it. This leaves sterile neutrinos in limbo, too compelling to abandon, yet too elusive to prove. Perhaps the most intriguing possibility is that sterile neutrinos aren't just dark matter but part of a richer hidden sector of particles. Some theories suggest they could interact with other invisible forces, creating a parallel, dark universe that only whispers to ours through gravity. It's a dizzying thought dark matter might not be a single particle but an entire shadow realm with sterile neutrinos as its faintest echo. For now, the hunt continues. Experiments like Katrin are pushing neutrino mass measurements to unprecedented precision, while upcoming telescopes like Athena may finally catch those ghostly X-ray signatures. Whether sterile neutrinos are the answer or another mirage, their story underscores a humbling truth. The universe's darkest secrets might be hiding in the particles we understand the least. What if the answer to dark matter has been lurking in the universe's oldest prisons, black holes forged not by collapsing stars, but in the chaos of the Big Bang itself? The primordial black hole theory dares to suggest that these ancient gravitational traps, born from density fluctuations in the first fractions of a second after creation, could be the invisible architects shaping our cosmos. Unlike their stellar counterparts, which form from dying stars, primordial black holes could range from the mass of a paperclip to thousands of suns, peppering the universe like unseen anchors. This idea isn't just elegant, it's radical. It sidesteps the need for exotic particles entirely, proposing instead that dark matter is simply gravity's masterpiece, hidden in plain sight. Picture the early universe as a bubbling cauldron of space-time, where pockets of ultra-dense matter collapsed directly into black holes. These relics would then drift through the ages, clustering in halos around galaxies, bending light with their gravity, and yet remaining utterly invisible. No particles to detect, no interactions to measure, just pure, unadulterated mass. But the theory faces a formidable obstacle: microlensing. When a massive object like a black hole passes in front of a distant star, its gravity acts as a lens, magnifying the star's light in a telltale flash. Surveys like Eros and Ogle have spent decades scanning millions of stars for these flickers, hunting for primordial black holes in our galactic neighborhood. Their conclusion: if black holes make up dark matter, they can't be in the sweet spot between the mass of an asteroid and 100 suns. Those would have been spotted by now. The universe seems to have vetoed the most obvious candidates, yet the door isn't completely closed. Some theorists argue primordial black holes might still lurk at either extreme, either so small they evaporate before we can see them thanks to Hawking radiation, or so massive they lens light too subtly for current surveys to catch. There's even a wild card. What if they're not black holes at all, but something stranger? Gravastars, hypothetical objects with exotic cores, or quantum fuzzballs predicted by string theory could mimic black holes' gravity while evading microlensing constraints. The most tantalizing clue might come from an unexpected source: gravitational wave detectors. When LIGO spotted merging black holes with masses that defied stellar formation models, some physicists wondered, could these be primordial remnants? Their unusual heft and spin align eerily with predictions for black holes forged in the Big Bang's fury. If future detections reveal a population of similarly odd mergers, it could resurrect the theory in spectacular fashion. Primordial black holes force us to confront a humbling possibility. After decades of hunting particles in underground labs and smashing atoms in colliders, dark matter might not be a particle at all. It could be the universe's oldest trick, a sea of frozen gravity waiting for us to think outside the quantum box. Whether the theory holds or crumbles, one thing's certain: the cosmos loves its illusions. What if dark matter doesn't exist at all? That's the radical proposition of modified Newtonian dynamics, or MUND, a theory that dares to rewrite the rules of gravity itself instead of invoking invisible particles. At its core, MUND suggests that our understanding of gravity is incomplete, especially in the feeble pull of galaxies' outer edges. When stars orbit too fast for visible matter to hold them, dark matter theorists see an unseen hand at work. MUND says Newton and Einstein simply missed a footnote. Gravity might strengthen slightly where it's weakest, bending the rules just enough to explain those whirling stars without dark matter's help. The idea isn't just provocative, it's shockingly effective in some cases. Take spiral galaxies, where Mund predicts rotation curves with uncanny precision, matching observed speeds without a shred of dark matter. It's as if the universe has a hidden safety net for gravity, one that activates only when forces dip below a critical threshold. For galaxies like the Milky Way, this tweak works eerily well, like fitting a missing piece into a puzzle we didn't realize was misaligned. Even more compelling, Mund predictions emerged before detailed observations confirmed them, a rare instance of theory leading the data. But the cracks start to show when Mund faces the cosmic wrecking ball of colliding galaxy clusters. The Bullet Cluster, that iconic smash-up where dark matter sailed ahead of visible matter, is Mund's nightmare scenario. No adjustment to gravity can explain why the mass, traced by gravitational lensing, separated from the gas unless something invisible carried it. Proponents scramble with workarounds, suggesting unseen neutrinos or tweaked versions of Mund, but these fixes feel like grafting dark matter back into the theory through the back door. Then there's the cosmic microwave background. The intricate patterns in the Big Bang's afterglow demand a precise mix of ordinary and dark matter to form the universe we see. Mund struggles to replicate these signatures without invoking some form of hidden mass, undermining its clean rejection of dark matter. Even its galactic successes aren't universal. Some dwarf galaxies follow Mund rules, while others defy them spectacularly, as if gravity's behavior changes on a whim. The harshest blow comes from cosmology itself. Dark matter isn't just a plug for galaxy rotations, it's the scaffolding for the entire cosmic web, the reason galaxies cluster the way they do. Mund offers no natural way to seed these structures in the early universe, leaving theorists to stack ad hoc assumptions where dark matter flows effortlessly. It's a bit like replacing a simple, universal force with a patchwork of exceptions, elegant in places but fraying at the edges. Yet Mund's persistence speaks volumes. Its ability to explain certain galactic phenomena with such simplicity keeps it alive in the scientific imagination, a reminder that even our most cherished theories might be approximations of something deeper. Perhaps the truth lies in a synthesis, some hybrid where gravity's quirks and dark particles coexist in a grander framework. Or perhaps Mund is a red herring, a beautiful dead end that illuminates just how strange the universe really is. One thing's certain, until dark matter is caught in a detector or Mund reconciles with the cosmos at large, the debate will rage on. And that's science at its best, a relentless pursuit of answers, even when they rewrite the questions. In 1998, two teams of astronomers made a discovery so shocking it earned them a Nobel Prize. They proved the universe wasn't just expanding, it was accelerating. Think about that for a second. If you throw a ball in the air, you expect it to slow down, pulled back by Earth's gravity. But imagine if that ball shot away faster and faster instead, defying every law you thought you knew. That's exactly what's happening on a cosmic scale. Distant supernova, the death throes of exploding stars, were fainter than they should have been, as if space itself had stretched even more than expected between them and us. The conclusion was inescapable. Some mysterious force, later dubbed dark energy, was pushing galaxies apart with ever-increasing strength. The implications rewrite our cosmic story. For decades, scientists assumed gravity would eventually slow the universe's expansion, leading to a big crunch, or at least a gradual coasting. Instead, we're witnessing a runaway cosmos where galaxies will one day vanish over the horizon of visibility, leaving future astronomers with a sky nearly empty of everything but darkness. What could possibly fuel this acceleration? The leading candidate is dark energy, an enigmatic pressure woven into the fabric of space itself. Unlike dark matter, which clumps around galaxies like invisible scaffolding, dark energy appears perfectly uniform, a repulsive force that grows stronger as the universe expands. Here's where things get weird. Einstein once proposed a similar idea, his infamous cosmological constant, to keep the universe static. He later called it his greatest blunder when Edwin Hubble proved expansion was real. Now, ironically, that discarded concept might hold the key. If dark energy behaves like Einstein's constant, it would mean empty space isn't empty at all but brimming with latent energy. The catch: quantum physics predicts this energy should be a staggering 10 to the power of 120 times stronger than what we observe. It's the worst mismatch in science, a discrepancy so vast it suggests we're missing something fundamental. Alternative theories abound. Maybe dark energy isn't constant but evolves over time, a dynamic field dubbed quintessence. Or perhaps gravity itself weakens across vast distances, mimicking acceleration without any dark energy at all. Then there's the unsettling possibility that we're seeing artifacts of our local cosmic environment, like mistaking a gentle hill for an endless slope. But the data keeps pointing back to acceleration. The Planck satellite's precision maps of the cosmic microwave background, combined with galaxy surveys like DAISY, all converge on the same conclusion. Dark energy dominates the universe's energy budget, yet its nature remains utterly opaque. What makes this mystery so profound is its stakes. If dark energy's strength increases, it could rip apart galaxies, stars, and even atoms in a big rip. If it fades, gravity might regain control, or it might be just the first chapter in a stranger story we've yet to imagine. One thing's certain: the accelerating universe isn't just a curiosity, it's a cosmic challenge, forcing us to confront how little we understand about the void we call home. Imagine calculating the height of a mountain and getting an answer taller than the observable universe. That's the scale of embarrassment physicists face with the cosmological constant problem, where theory and reality disagree by a factor of 1 followed by 120 zeros. It's not just a gap in our knowledge, it's a yawning chasm, often called the worst prediction in the history of science. Here's the core of the catastrophe. Quantum physics tells us that empty space should be a seething foam of virtual particles, constantly flickering in and out of existence. Each of these fleeting particles contributes a tiny bit of energy to the vacuum, and when you add them all up, the result is a number so colossal it should have ripped space-time apart microseconds after the Big Bang. Yet when we look at the actual universe, dark energy's measured effect is staggeringly small, like comparing the output of a nuclear reactor to a single candle flame. This isn't just a rounding error, it suggests something fundamental is missing from our understanding. Maybe the infinite contributions from quantum fields mysteriously cancel out, leaving only a faint residue we call dark energy. Or perhaps we've misunderstood vacuum energy entirely, mistaking mathematical abstraction for physical reality. Either way, the discrepancy is so vast it's like hearing a symphony, but only detecting the vibration of a single violin string. The craziest part: this isn't some fringe speculation. The cosmological constant problem strikes at the heart of quantum field theory and general relativity, the twin pillars of modern physics. Einstein originally introduced the constant as a fudge factor to keep the universe static, but Hubble's discovery of cosmic expansion made it seem unnecessary. Now, ironically, it's back with a vengeance as the leading explanation for dark energy, just with a value 120 orders of magnitude smaller than quantum calculations suggest. It's as if the universe is whispering, "You're close, but you've missed something enormous." Some theorists argue the answer lies in the multiverse, a vast landscape of universes, each with randomly determined constants. In most, the cosmological constant is so large that galaxies never form. We just happen to live in one of the rare habitable outliers where it's oddly tiny. Others propose radical modifications to quantum gravity or hidden symmetries that suppress vacuum energy. But so far, no solution feels satisfying. The cosmological constant problem isn't just a puzzle, it's a flashing neon sign that our most cherished theories are incomplete. What makes this so thrilling and frustrating is that dark energy isn't some abstract concern. It's the dominant force shaping the universe's fate. If the vacuum energy were even slightly stronger, matter would never have clumped into stars and galaxies. Slightly weaker, and gravity would have collapsed everything back into a singularity eons ago. We exist in a razor-thin sweet spot, and no one knows why. The cosmological constant problem isn't just about numbers on a page. It's about understanding why the universe allows us to be here at all. Among all the fates awaiting our universe, none chills the blood quite like the Big Rip, a scenario where dark energy doesn't just push galaxies apart but grows infinitely stronger, shredding spacetime itself. Imagine a force that starts by tearing clusters apart, then galaxies, then stars, until finally, in a final apocalyptic moment, even atoms are ripped into unbound particles. This isn't science fiction, it's the phantom energy hypothesis, a realization that dark energy might not play nice forever. The math behind this cosmic horror story hinges on one terrifying variable, the equation of state parameter denoted as W. For dark energy to remain benign, this value should hover near -1, like Einstein's cosmological constant. But phantom energy proposes something far worse, a W less than -1, meaning dark energy's repulsive power escalates as space expands. It's the difference between a balloon inflating steadily and one that stretches faster until its rubber bursts under its own tension. The universe, in this case, wouldn't just fade into cold isolation, it would explode from within. Evidence for such a grim finale is scarce but unsettling. Observations of supernova and baryon acoustic oscillations haven't yet ruled out phantom energy entirely. Some measurements even flirt with values slightly below -1, though error bars leave room for doubt. The real smoking gun would come from spotting an accelerating expansion rate, not just consistent but growing fiercer over time. Projects like the Dark Energy Spectroscopic Instrument are hunting for exactly this, mapping millions of galaxies to track whether dark energy's grip is tightening. Yet the implications stretch beyond astronomy. Phantom energy challenges core assumptions in physics. If it exists, it violates the so-called null energy condition, a sacred principle asserting that energy density can't dip below zero. Break that rule, and you invite time-traveling wormholes or universes born from nothing, wild possibilities that make the Big Rip seem almost mundane by comparison. Why hasn't this unraveling begun yet? Time scales offer grim comfort. If phantom energy is real, the Big Rip might wait tens of billions of years, long after the sun dies. But on cosmological clocks, that's a blink. What makes phantom energy so unnerving isn't just its destructive potential, it's the reminder that dark energy, the mystery dominating our universe's fate, could still have surprises darker than we dare imagine. The cosmological constant presents dark energy as a fixed feature of space, an unchanging background hum that drives the universe apart. But what if it's not so constant after all? Enter quintessence, a dynamic cousin to dark energy that could rewrite our cosmic narrative. Unlike the stubborn uniformity of Einstein's cosmological constant, quintessence proposes a field that evolves over time, its strength waxing or waning as the universe ages. Imagine a cosmic dial that subtly adjusts its setting, sometimes pushing galaxies apart gently, other times with surprising force. This isn't just a tweak to the equations, it's a fundamental shift in how we envision the fabric of reality. The allure of quintessence lies in its flexibility. The cosmological constant's rigid predictability struggles to explain why dark energy's influence seems so perfectly fine-tuned to allow galaxies and life to exist. Quintessence, on the other hand, could naturally settle into its current state through cosmic evolution, like a ball rolling to rest at the bottom of a valley. Some models even suggest it once played nice with dark matter, slowing the universe's early expansion before switching roles to accelerate it. This dance between attraction and repulsion might solve mysteries the cosmological constant leaves gaping, like why dark energy's dominance began relatively recently in cosmic terms. Testing this idea demands tools that peer deeper than ever into the universe's past. Upcoming telescopes like the Vera C, Rubin Observatory, and the European Space Agency's Euclid mission are designed to map billions of galaxies across cosmic time, hunting for minute changes in the rate of expansion. If dark energy were truly constant, those distant galaxies should follow a predictable drift. But if quintessence is at work, astronomers might spot subtle speed-ups or slowdowns, cosmic hesitations betraying a field in flux. Even more telling would be discrepancies in how galaxy clusters form. Quintessence's evolving push would leave fingerprints in the large-scale structure of the universe, altering how matter clumps together over eons. Yet quintessence isn't without its skeptics. Introducing a dynamic field means adding complexity, new particles, interactions, or energies that demand justification. Worse, many quintessence models risk drifting into what theorists call fine-tuning, where the field's behavior must be precisely calibrated to match observations, echoing the very problems it tries to solve. And then there's the phantom menace. Some quintessence variants could theoretically spiral into negative energy densities, triggering a catastrophic big rip. The line between solution and speculation remains frustratingly thin. What makes this hypothesis so compelling isn't just its potential answers, it's the sheer audacity of the questions it raises. If quintessence is real, then dark energy isn't a static stage for cosmic drama but an active player, evolving alongside the universe it shapes. Future telescopes won't just be mapping galaxies, they'll be detectives piecing together the biography of a force we've only begun to name. Whether quintessence survives those tests or crumbles under scrutiny, one truth remains: the universe's greatest mysteries refuse to sit still. Astronomers are locked in a cosmic tug-of-war over one of the most important numbers in the universe, the Hubble constant, which measures how fast space is expanding. The problem: two of our most trusted methods for calculating this critical value keep giving different answers, and the gap between them is growing wider with each new measurement. It's like using two thermometers to check the same patient's fever. One reads 101 degrees, the other 104. That discrepancy might not sound like much, but in cosmology, it's enough to spark a full-blown crisis. First, there's the early universe approach. By studying the cosmic microwave background, the afterglow of the Big Bang, missions like Planck have pinned the expansion rate at roughly 67 kilometers per second per megaparsec. That means for every 3 million light-years you look deeper into space, galaxies appear to recede 67 kilometers per second faster. But then we have the late universe method, using pulsating stars called Cepheids and cataclysmic supernova as cosmic yardsticks. Teams like the one behind the Hubble Space Telescope's SOES project consistently get a higher number, around 73. The difference seems small, but after 13 billion years of cosmic expansion, that gap balloons into a glaring inconsistency. So who's right? If the Planck measurements are off, it could mean we've misunderstood the physics of the early universe. Perhaps dark energy isn't constant after all, or maybe neutrinos played a bigger role than we thought. But if the local measurements are flawed, the implications are just as profound. Maybe Cepheid stars, our go-to distance markers, aren't as reliable as we've assumed, or supernova behave differently in modern galaxies than they did in the past. Then there's the tantalizing third option: neither side is wrong. The discrepancy might signal entirely new physics, like an undiscovered particle that briefly altered the expansion rate in the universe's adolescence. Some theorists propose early dark energy, a fleeting field that revved up expansion before fading away, leaving no trace but this stubborn tension. Others wonder if dark matter's properties evolved over time, subtly tweaking gravity's grip on the cosmos. The stakes couldn't be higher. If this tension holds, it could mean our standard model of cosmology, the very framework we use to understand the universe's birth, growth, and fate, is missing a crucial piece. Upcoming telescopes like the James Webb Space Telescope and the Nancy Grace Roman Observatory are already hunting for answers, scrutinizing Cepheids and supernova with unprecedented precision. Meanwhile, novel techniques like tracking gravitational waves from colliding neutron stars offer fresh ways to measure cosmic distances without relying on starlight at all. What makes this mystery so electrifying isn't just the numbers, it's the realization that we might be standing at the edge of a paradigm shift. The Hubble tension isn't just a clerical error, it's a flashing signpost pointing toward uncharted physics. Whether it's flawed data or a fundamental breakthrough waiting to happen, one thing's certain: the universe is still keeping its deepest secrets close. What if everything we think we know about dark energy is just an illusion? That's the unsettling premise of the void hypothesis, the idea that we might be living in a vast, underdense bubble of space where the local emptiness distorts our cosmic measurements. Imagine standing in a valley surrounded by mountains. Your perspective would make the world seem far emptier than it really is. Now scale that up to galactic proportions. If our Milky Way resides in an unusually sparse region of the universe, the accelerated expansion we attribute to dark energy could be nothing more than a trick of our lopsided vantage point. This isn't just a wild guess, it's a direct challenge to the Copernican principle, the foundational belief that Earth, and by extension our galaxy, holds no special place in the cosmos. For centuries, this idea has guided astronomy, assuring us that the universe looks roughly the same everywhere. But the void hypothesis dares to ask, what if it doesn't? If our neighborhood is a rare cosmic desert, the apparent acceleration of distant galaxies could simply be because we're sitting in a gravitational ditch, causing the surrounding denser regions to pull away faster than expected. No dark energy required, just a colossal case of bad luck in our cosmic address. Evidence for this radical idea comes from peculiar observations. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing filamentary structures punctuated by enormous voids spanning hundreds of millions of light years. Some of these voids, like the KBC supervoid, a staggering 1 billion light-year wide emptiness, seem suspiciously aligned with our position. Proponents argue that such a void could mimic dark energy's effects, with light from distant supernova dimming as it climbs out of our gravitational depression, creating the illusion of acceleration. But the void hypothesis isn't without its critics. To explain dark energy's apparent strength, the void would need to be absurdly large, nearly a third of the observable universe, and profoundly empty, defying statistical expectations for cosmic structure. Even then, it struggles to explain other dark energy signatures, like the precise patterns in the cosmic microwave background or the way galaxy clusters clump together. Worse, such a void would leave telltale imprints on the cosmic microwave background's temperature, something Planck's meticulous maps haven't found. The most damning counterargument, though, comes from the sheer improbability of our placement. A void big enough to fool us would be a 1 in a million cosmic fluke, violating the very Copernican humility the hypothesis seeks to exploit. It's like winning the lottery 10 times in a row possible, but staggeringly unlikely. Still, the idea lingers because it highlights a deeper truth. Our cosmic models are only as good as our assumptions. Every measurement we make is filtered through layers of interpretation, and the void hypothesis forces us to question whether we've missed a fundamental bias in our data. For now, the scales tip against the void, but its real value isn't in being right, it's in reminding us that even our most cherished principles must survive relentless scrutiny. Dark energy may still be the simplest explanation, but in a universe this vast, it's worth checking whether we're the ones standing in the shadow. What if dark energy and dark matter aren't just passive cosmic roommates but locked in an intricate dance? The idea that these two invisible forces might interact isn't just speculative, it's a radical reimagining of how the universe evolves. Picture two actors on a stage, one pulling galaxies together while the other pushes them apart. Now imagine they're whispering to each other, subtly altering each other's performance. If even a fraction of that interaction is real, it could unravel mysteries from galaxy formation to the universe's ultimate fate. Take the coincidence problem, the puzzling fact that dark energy's dominance began just as dark matter's influence waned. It's as if the cosmos orchestrated a perfect handoff, one force stepping back as the other stepped forward. Some theorists argue this timing is too precise to be accidental. If dark energy and dark matter exchange energy or influence each other's behavior, it could explain why their eras align so neatly. One compelling model suggests dark matter decays into dark energy over time, like ice melting into water, gradually shifting the universe's balance. Others propose an interaction where dark energy siphons strength from dark matter, accelerating its own expansion at the expense of gravity's grip. The consequences ripple across cosmic history. In the early universe, dark matter's clumping forged the first galaxies. If dark energy subtly meddled with that process, perhaps by slowing dark matter's aggregation, it could explain why some galaxies are smaller or more diffuse than simulations predict. Observations of galaxy clusters like El Gordo, whose immense size defies standard models, might hint at such an interaction. Even the cosmic web's intricate filaments could bear scars of this unseen tug-of-war, with voids stretching wider and faster than expected if dark energy drains dark matter's cohesion. Then there's the Hubble tension, the discrepancy in cosmic expansion rates. If dark energy and dark matter interact, their shifting dynamics might have briefly altered the universe's growth spurt, leaving today's measurements in conflict. It's a stretch, but not impossible. Future galaxy surveys like Euclid or Daisy could spot telltale irregularities in large-scale structure patterns that betray an ancient exchange between these shadowy forces. The most tantalizing possibility, these interactions might not be constant. Dark energy could wax and wane in response to dark matter's distribution, creating feedback loops that accelerate or break expansion in cycles. Such behavior would upend our static view of dark energy, transforming it from a passive backdrop to an active participant in cosmic evolution. Of course, skepticism abounds. Without direct evidence, these theories remain elegant speculation. Yet the mere possibility forces us to confront a humbling truth. The universe's greatest mysteries might not live in isolation. Dark energy and dark matter could be two sides of the same enigma, a duality we're only beginning to trace. As probes delve deeper into the cosmos's hidden layers, each new observation brings us closer to answering whether these forces are strangers or siblings, shaping the universe in ways we've yet to dream. The fate of the universe hinges on a mystery we can't even see: dark energy's next move. Will it remain a steady force, fade into obscurity, or turn catastrophic? The answer paints three radically different endings for reality itself. First, there's the heat-death scenario, a slow, cold unraveling where dark energy keeps expanding space at its current pace. Galaxies will vanish over the cosmic horizon, stars will burn out, and over trillions of years, even black holes will evaporate via Hawking radiation. The universe becomes a vast graveyard of dispersed particles, too far apart to ever interact again. It's not an explosion or a collapse, but a whisper fading into absolute zero. Then there's the nightmare option, the Big Rip. If dark energy strengthens over time, transforming into so-called phantom energy, it could tear the cosmos apart atom by atom. Picture a relentless stretching of space-time itself, first separating galaxy clusters, then galaxies, then solar systems. In the final moments, stars and planets would be shredded, followed by molecules, then atoms, their nuclei unable to withstand the exponential expansion. The universe wouldn't just end, it would dissolve. Some models peg this doomsday as early as 22 billion years from now, a blink on cosmic timescales. But there's a twist that turns this narrative inside out: cyclic universes. What if dark energy isn't forever? Certain theories suggest it could decay, reversing into an attractive force that pulls everything back together in a big crunch. Matter and energy would collapse into a singularity, potentially triggering a new Big Bang, a cosmic reset. This isn't science fiction. Equations in string theory and loop quantum gravity allow for such rebounds. The catch: we'd need dark energy to be fundamentally unstable, a temporary phase in the universe's life cycle rather than a permanent fixture. The terrifying truth: we have no idea which path we're on. Every measurement of dark energy's behavior carries error bars wide enough to hide multiverses. Even subtle shifts in its strength, changes too small for current telescopes to detect, could flip the script entirely. Projects like the Dark Energy Spectroscopic Instrument are racing to track expansion rates across billions of years, hunting for clues in the light of ancient quasars. But for now, the universe's ultimate destiny remains locked in a vault we've only just begun to crack open. What makes this uncertainty so profound isn't just the scale of the stake, it's the realization that dark energy might not play by fixed rules. Like a cosmic wild card, it could switch strategies at any moment, leaving our predictions in the dust. Whether the universe winds down, blows apart, or reboots anew, one thing's certain: the final chapter won't just be an ending. It'll be the ultimate reveal of forces we're only beginning to name. If dark energy is the universe's greatest riddle, then quantum gravity might be its most promising and frustrating solution. At the heart of this enigma lies a collision between two titans of physics: Einstein's general relativity, which paints gravity as the curvature of space-time, and quantum mechanics, the rules governing the subatomic world. Individually, these frameworks are breathtakingly accurate, but when they meet, chaos erupts, especially in the presence of dark energy's mysterious push. The vacuum of space, according to quantum theory, should bubble with energy, yet general relativity treats it as inert. This clash isn't just academic. It's the reason dark energy's observed strength is a factor of 10 to the power of 120 smaller than quantum calculations predict. It's like expecting a tsunami and getting a ripple instead. String theory, the leading candidate for a quantum gravity framework, offers a tantalizing escape hatch. In this universe, particles aren't dots but tiny, vibrating strings, and the fabric of reality might have hidden dimensions curled into microscopic loops. Some versions of the theory naturally accommodate dark energy as a feature of these extra dimensions, a cosmic stabilizer emerging from the geometry of space itself. Imagine dark energy as the tension in a stretched rubber sheet. The more dimensions flex, the more energy permeates the vacuum. But here's the catch: string theory isn't one theory. It's a landscape of maybe 10 to the 500 possible solutions, each describing a universe with different constants. Finding the one that matches ours is like searching for a needle in a multiverse of haystacks. Even if string theory holds the answer, testing it seems impossible with current technology. The energy scales required to probe these extra dimensions are billions of times beyond what particle colliders like the LHC can achieve. Quantum gravity's fingerprints might linger in the echoes of the Big Bang or the glow of evaporating black holes, but spotting them would demand telescopes and sensors we've yet to invent. It's a cruel irony. The very theory that could unify physics might forever hover beyond experimental reach. Yet alternatives exist. Loop quantum gravity, string theory's rival, suggests spacetime isn't smooth but woven from tiny, indivisible loops. In this view, dark energy could arise from the quantum edges of this fabric, like static building up in a cosmic sweater. Some models even predict dark energy's strength would fade over time, turning the universe's acceleration into a temporary phase. But without observational evidence, these ideas remain mathematical daydreams. The deeper we dig, the clearer the dilemma becomes. Quantum gravity could explain dark energy, or it could complicate the picture beyond repair. Until we bridge the gap between theory and experiment, dark energy will remain a paradox, a force so pervasive it shapes the cosmos, yet so elusive it defies every tool we've built to understand it. The universe, it seems, enjoys playing hard to get. Here's something eerie to consider. What if dark energy's precise, delicate value isn't a cosmic accident, but a prerequisite for our existence? This unsettling idea, known as the anthropic principle, suggests that the universe's fundamental constants, including dark energy's mysteriously tiny strength, are tuned within razor-thin margins to allow life to emerge. It's like discovering the oxygen level in Earth's atmosphere is exactly 21%, and realizing that even a few percentage points higher or lower would make complex life impossible. But here's the twist. Applying this logic to dark energy forces us to confront whether the universe is somehow designed for life, or if we're just lucky winners in a cosmic lottery with infinite losing tickets. Take the numbers first. Dark energy's observed density, about 120 orders of magnitude weaker than quantum field theory predicts, isn't just a random fluke. If it were slightly stronger, the universe would have expanded too rapidly for galaxies to form, leaving space an empty, lifeless void. Slightly weaker, and gravity would have crumpled everything back into a big crunch before stars could ignite. The window for life-friendly values is absurdly narrow, like balancing a pencil on its tip in a hurricane. For some theorists, this precision screams fine-tuning, raising uncomfortable questions. Are we staring at evidence of a deeper principle, or just survivorship bias on a cosmic scale? Critics pounce on this logic. They argue the anthropic principle is less a scientific explanation and more a philosophical shrug, a way to dodge the hard work of finding physical mechanisms. If we accept that constants are just right for life because we're here to observe them, science risks sliding into lazy teleology. Imagine a puddle marveling at how perfectly its hole fits its shape, unaware of the countless other holes it could have occupied. This puddle analogy, coined by Douglas Adams, cuts to the heart of the debate. Does the universe care about life, or does life merely adapt to the universe's indifference? Yet the anthropic principle gains traction when paired with the multiverse. In an infinite ensemble of universes, each with randomly determined constants, statistically some will inevitably land in the life-permitting sweet spot. We, of course, find ourselves in one of those rare, habitable bubbles no creator required. String theory's landscape of possible vacua, with its 10 to the 500 potential universes, offers a mathematical playground for this idea. But the multiverse brings its own baggage. If it's untestable, is it even science, or just metaphysical speculation dressed in equations? The philosophical stakes are staggering. If the anthropic principle holds, it reshapes humanity's place in the cosmos not as central players, but as fleeting witnesses to a universe that, against all odds, allowed us to exist. It whispers that our very presence is a filter, winnowing reality down to the sliver we can perceive. Whether that's profound or profoundly unnerving depends on who you ask. For now, dark energy's eerie precision remains either a clue to deeper laws or the ultimate cosmic coincidence, and the answer might redefine not just physics, but what it means to ask why at all. What if the universe isn't three-dimensional at all? The holographic principle dares to suggest that everything we perceive, stars, galaxies, even the vast expanse of dark energy stretching the cosmos, might be nothing more than a two-dimensional projection, like a cosmic mirage. This isn't science fiction. It's a mathematically rigorous idea born from black hole physics, where the information describing every object swallowed by a singularity isn't lost but encoded on its two-dimensional surface. Extend this logic to the entire universe, and suddenly, dark energy's mysterious presence takes on a surreal new meaning. It could be the artifact of a deeper, flatter reality bleeding through. The math behind this is both elegant and mind-bending. In the late 1990s, physicists like Gerard T. Hooft and Leonard Susskind realized that the maximum entropy, the information capacity, of any region of space doesn't scale with its volume but with its surface area. It's as if a library's entire collection could be stored on its walls instead of filling its shelves. Apply this to cosmology, and dark energy's uniformity makes eerie sense. If the universe is fundamentally a two-dimensional information field, its apparent acceleration could stem from how that data is projected into three dimensions, like a hologram whose pixels subtly warp over time. String theory lends weight to this with its AD/CFT correspondence, a duality where a higher dimensional anti-de Sitter space, a universe with negative curvature, can be perfectly described by a lower dimensional quantum field theory. While our universe isn't AD/S, the principle hints that dark energy's effects might emerge from similar informational boundaries. Imagine dark energy as the processing cost of rendering a three-dimensional cosmos from a two-dimensional code, with expansion representing the system's growing computational overhead. Critics point out the holographic principle remains untested. Its beauty lies in equations, not evidence. Yet tantalizing clues linger. The cosmic microwave background's fluctuations, for instance, show patterns that some argue resemble a pixelated hologram's noise. And if spacetime is indeed pixelated at the Planck scale, future quantum gravity experiments might detect its graininess, like spotting the dots in a newspaper photo up close. The real shock: if the holographic principle is correct, dark energy isn't a force but a glitch, a side effect of reality itself being an illusion. It's a radical reimagining of existence, where the universe's greatest mystery reduces to a cosmic rounding error in the math of dimensionality. Whether this idea holds or collapses under scrutiny, one thing's clear: the deeper we probe dark energy, the less it feels like a substance and more like a signature, one that might be written in a language we're only beginning to decode. Dark energy's unnervingly precise value might not be a fluke, it could be a cosmic address. Among the infinite universes predicted by string theory's landscape, ours just happens to occupy the narrow slice where dark energy's strength allows galaxies, stars, and life to exist. This is the multiverse's answer to the fine-tuning problem. In a sea of possibilities, most universes drown in runaway expansion or collapse into singularities, while ours hits the gravitational jackpot. But this elegant solution comes with a catch. It might be untestable, pushing dark energy's mystery beyond the reach of science as we know it. Picture a cosmic casino where every spin of the wheel creates a new universe with randomly determined constants. In 99.9% of them, dark energy's value is too high, ripping spacetime apart before matter can clump into atoms. In others, it's too weak, causing gravity to crumple everything back into a big crunch before the first stars ignite. Only in a vanishingly small fraction like ours does dark energy land in the Goldilocks zone. This anthropic selection sounds tidy, but it raises a thorny question. If most universes are lifeless wastelands, how do we prove ours isn't just a statistical outlier? Critics argue this multiverse logic borders on metaphysics. Without a way to observe alternate universes or measure their properties, the theory can't be falsified. It's like claiming invisible dragons fine-tune the cosmos. Even string theory's vaunted landscape of 10 to the 500 possible vacua offers no roadmap to verification. Those extra dimensions might be mathematically beautiful, but if they're permanently hidden from experiment, do they qualify as science or philosophy? The line between groundbreaking insight and unfalsifiable speculation blurs uncomfortably, yet the multiverse hypothesis isn't entirely without fingerprints. If our universe is one bubble in a froth of others, collisions between neighboring realms could leave scars in the cosmic microwave background, anomalous cold spots or concentric ripples in the afterglow of the Big Bang. Satellite missions like Planck have hunted for these bruises, but so far the evidence is murky at best. another approach probes the quantum nature of spacetime itself. If the fabric of reality is pixelated at the tiniest scales, as loop quantum gravity suggests, those grains might carry echoes of other universes' births. The real irony, dark energy might hold the key to unlocking the multiverse or burying it forever. If future telescopes uncover dynamic shifts in its strength, it could hint at interactions with unseen dimensions or sibling universes. Conversely, if dark energy remains stubbornly constant, the multiverse explanation starts to feel like a narrative convenience. Either way, the stakes are cosmic. We're not just deciphering dark energy's role in our universe, we're grappling with whether the question, why this value, even has an answer, or if we're stuck marveling at a dice roll frozen in time. Zoom out far enough and the universe reveals its hidden architecture, a vast glittering web of galaxies strung along invisible threads, stretching billions of light years across the void. This cosmic web, with its dense knots and gossamer filaments, didn't assemble by accident. It's the handiwork of dark matter's relentless pull, sculpting the universe's structure while dark energy stretches the canvas beneath it. Picture two cosmic artists working in tandem, one meticulously carving valleys and mountains, the other steadily expanding the landscape so fast that the sculptor's hands must race to keep up. Start with dark matter's role, the universe's unseen architect. In the aftermath of the Big Bang, tiny quantum fluctuations seeded slight variations in density across the newborn cosmos. Dark matter, responsive only to gravity, began clustering around these overdensities, drawing ordinary matter along for the ride. Over billions of years, these clumps grew into towering filaments, intersecting at nodes where galaxy clusters now blaze like metropolises. The result, a labyrinthine network where galaxies align along dark matter's gravitational highways, tracing patterns eerily similar to neurons in a brain or veins in a leaf. The Sloan Digital Sky Survey's 3D maps capture this web in stunning detail, showing thousands of galaxies flocking to filaments as if pulled by some invisible tide. Yet, threading between these structures, dark energy plays the opposite game. Where dark matter builds, dark energy dismantles, not by tearing structures apart, but by stretching the space between them so fiercely that eventually, even the web's tightest knots will vanish over the horizon. Imagine building a sandcastle while the tide rushes out. Your creation might stand tall for now, but the seafloor beneath it is sliding irretrievably away. That's the fate of galaxy clusters in an accelerating universe. Dark energy doesn't destroy, it isolates, leaving islands of matter adrift in an ever-widening ocean of nothingness. The irony is exquisite. Dark matter's gravity forges the cosmic web, while dark energy ensures it will one day unravel. Without dark matter, galaxies would never have formed. Without dark energy, they'd clump into a suffocating mass. Their interplay is a delicate dance, fine-tuned to a degree that still baffles cosmologists. Too much dark matter and the universe collapses inward. Too much dark energy and it flies apart before stars ignite. We exist in the razor-thin sliver where these forces balance just long enough for complexity to emerge. What's even stranger is how recently dark energy took the lead. For 9 billion years, dark matter's gravity dominated, weaving the web we see today. Only in the last 5 billion years did dark energy's push overpower it, flipping the cosmic script. Future astronomers, if any exist, will witness a far lonelier cosmos, one where the web's threads snap, its galaxies fading into darkness. For now, though, we're living in the golden age of cosmic cartography, mapping a structure whose architects remain as elusive as shadows. The cosmic web isn't just a testament to dark matter and dark energy's power, it's a snapshot of a fleeting equilibrium, a moment in the universe's life when both forces still leave their mark. To understand dark matter and dark energy, we have to rewind the cosmos back to its first frantic moments when the entire universe was smaller than a single atom and laws of physics as we know them flickered in and out of existence. This isn't just a story about how everything began. It's a forensic investigation into how the invisible scaffolding of reality might have taken shape. The leading theory, cosmic inflation, suggests that in the first trillionth of a second, space itself expanded faster than light, stretching quantum fluctuations into the seeds of galaxies. But here's the twist: inflation's equations work too well. They predict a universe filled with far more structure than we observe, unless something intervened to smooth things out. That something might be dark matter acting as a cosmic dampener to inflation's runaway expansion. Consider baryogenesis next, the puzzle of why matter dominates over antimatter in our universe. For every billion particles of antimatter created in the Big Bang, there were 1,000,000,001 particles of matter. That tiny excess is everything: stars, planets, us. But the math doesn't add up without help. Some theories propose that dark matter particles interacting weakly with ordinary matter could have tipped the scales. Picture a seesaw in the early universe. As dark matter particles decayed or collided, they might have generated the precise imbalance that made our existence possible. It's a tantalizing link between the visible and invisible worlds, suggesting dark matter isn't just a bystander but an active participant in shaping cosmic history. Then there's the mystery of the dark sector, a hypothetical shadow realm where dark matter and dark energy might obey their own set of rules, complete with hidden forces and particles. If true, the early universe would have been a battleground between these dark interactions and the familiar forces we know. Think of it like a double-stage rocket. First, inflation launches the cosmos into existence. Then, the dark sector's dynamics fine-tune the outcome, leaving behind the universe we recognize. Clues might lie in gravitational waves from the Big Bang, primordial ripples that could carry echoes of dark matter's first movements. Experiments like LISA and pulsar timing arrays are listening for these whispers, hoping to decode a narrative written in space-time itself. Yet the most provocative question remains: did dark energy exist from the beginning, or did it emerge later like a cosmic latecomer? Some models suggest it's the remnant energy of empty space, a relic of quantum fields that froze during inflation. Others argue it's a phase transition like water turning to ice that flipped on 5 billion years ago. The answer could redefine our understanding of time. If dark energy's strength has changed over the eons, it implies the laws of physics aren't static but evolve alongside the universe. Every second that passes, the afterglow of the Big Bang fades further into the void, taking with it clues about these early moments. But with next-generation telescopes and particle detectors, we're not just chasing shadows anymore. We're piecing together a story where dark matter and dark energy aren't just footnotes but central characters in the epic of existence. The early universe's secrets aren't lost. They're written in the gaps between galaxies, waiting to be read. Every mystery reaches its turning point, and for dark matter and dark energy, that moment is now. A new wave of experiments, armed with technology straight out of science fiction, is poised to peel back the universe's deepest secrets. At the forefront is the Vera Rubin Observatory in Chile, a behemoth with a mirror the size of a small house and a camera boasting 3.2 billion pixels. Starting in 2025, it will scan the entire southern sky every few nights, capturing changes so subtle they'd escape lesser instruments. Imagine tracking billions of galaxies in real time, watching for distortions caused by dark matter's gravity or shifts in brightness that might reveal dark energy's grip tightening. This isn't just observation, it's a cosmic stakeout, with the universe's most elusive suspects in the crosshairs. Then there's Euclid, the European Space Agency's dark universe detective. Launched in 2023, this space telescope is mapping the cosmos in infrared and visible light, tracing the invisible scaffolding of dark matter through its gravitational lensing effects. But Euclid's real genius lies in its precision. It can measure the shapes and positions of galaxies with such accuracy that even the faintest warp in space-time becomes a clue. Over 6 years, it'll survey a third of the sky, building a 3D atlas of dark matter's distribution, and possibly spotting anomalies that hint at dark matter particles interacting in ways we've never seen. Meanwhile, the Dark Energy Spectroscopic Instrument, DESI for short, is taking a radically different approach. Perched atop a telescope in Arizona, DESI isn't just looking at galaxies, it's dissecting their light. By capturing the spectra of 35 million galaxies and quasars, it's creating the most detailed map yet of the universe's expansion over 11 billion years. The goal: to catch dark energy in the act, revealing whether its strength has changed over time. If DESI finds even a slight variation, it could confirm theories like quintessence or unveil something entirely new. But the real game changer might be lurking underground. Experiments like LUX Zeppelin and Darwin are pushing the limits of dark matter detection, using vats of liquid xenon so pure they can sense a single particle collision. These aren't just upgrades, they're leaps into uncharted sensitivity. If dark matter particles interact with ordinary matter at all, these detectors are now fine-tuned enough to catch them. And if they don't, that silence would be just as revolutionary, forcing us to abandon decades of assumptions and rethink dark matter's nature entirely. The most daring wildcard comes from quantum technology. Projects like AION and MAGIS are preparing to use atom interferometry, exploiting the wave nature of atoms, to detect gravitational waves and possibly even dark matter's faint ripples in spacetime. It's a long shot, but if successful, it could open an entirely new window into the invisible universe. What ties these efforts together isn't just their ambition, but their timing. For the first time in history, we're not just guessing about dark matter and dark energy. We're hunting them with tools capable of delivering answers within years, not decades. Whether it's a rogue signal in a xenon tank, a twist in Euclid's cosmic map, or a surprise in DESI expansion data, one thing's certain: the universe's greatest mysteries are finally within reach. And when the breakthrough comes, it won't just solve a puzzle, it'll rewrite the story of everything. What does it mean to call something real when 95% of reality refuses to interact with us? Dark matter and dark energy don't just defy detection, they upend the very foundation of how we define existence. For centuries, science operated on the assumption that to understand the universe, we needed only to observe and measure it. But these twin enigmas force a humbling admission. The tools we've relied on, light, electromagnetism, even our own senses, are blind to the cosmos's true nature. Imagine spending your life studying ocean waves while remaining oblivious to the water itself. That's the philosophical vertigo these mysteries induce, the realization that what we perceive as the universe might be little more than its foam. Consider how our definitions of matter and energy crumble under scrutiny. Matter, as we've always known it, is tangible, it collides, reflects light, occupies space. Yet dark matter shatters that intuition, proving mass can exist without any of these traits. Energy, in classical physics, is measurable through work or heat. Dark energy laughs at such notions, exerting measurable force while leaving no detectable trace of its mechanics. It's as if we've been handed a physics textbook where the final chapters aren't just blank, but written in ink visible only under alien starlight. This invisibility carries deeper implications. If the majority of reality operates beyond perception, how can we trust empirical methods at all? The scientific method hinges on observation and reproducibility, but dark matter and dark energy mock these principles, revealing their presence only through gravitational sleight of hand. Some philosophers argue this demands a new epistemology, a framework where indirect evidence holds equal weight to direct measurement. Others see a kinship with quantum mechanics, where particles exist in probabilistic smears until observed. Perhaps dark phenomena are the cosmic scale's version of superposition, real, yet resistant to classical observation. The existential stakes ripple outward. Human curiosity has always sought to demystify the universe, to render it knowable. But dark energy's accelerating expansion suggests a future where most galaxies will vanish beyond an unreachable horizon, their light stretched into oblivion. In time, all evidence of the cosmos's true scale will disappear, leaving any future civilizations with a night sky nearly empty. Their science might conclude the universe is small, static, and lonely, a cruel irony given the vastness we're privileged to witness now. Does knowledge, then, have an expiration date? Are we uniquely positioned in cosmic history to glimpse the full theater before the curtain falls? These aren't just academic musings. They reshape how we value exploration. If reality's bulk is inherently unknowable, does that devalue the pursuit, or does it elevate the fragments we can grasp? The poet Rilke once advised living the questions themselves, a mantra that resonates here. Dark matter and dark energy may never yield to full understanding, but the act of grappling with them expands what it means to be curious, to be human in a universe that withholds its deepest truths. Perhaps the greatest revelation isn't about the cosmos, but ourselves. Faced with forces that defy categorization, we're forced to confront the limits of language, of logic, even of imagination. The very terms dark matter and dark energy betray our helplessness, placeholder labels for voids in understanding. Yet in that uncertainty lies a paradoxical gift, the reminder that mystery isn't failure but an invitation. An universe that could be fully known would be smaller than one that forever whispers, "There's more." There comes a point in every great scientific quest when we must ask, not just what we might discover, but whether some answers are destined to remain forever out of reach. Dark matter and dark energy present this dilemma in its purest form. Cosmic riddles woven so deeply into the fabric of reality that unraveling them might demand tools and perspectives we haven't yet imagined. Consider how long these mysteries have persisted. Fritz Zwicky first proposed dark matter in 1933 after noticing galaxies moving too fast for their visible mass. Nearly a century later, despite building detectors deep underground, launching space telescopes, and simulating universes on supercomputers, we're still staring at the same invisible elephant in the room. This isn't for lack of trying. Modern science operates on a scale that would astonish pioneers like Zwicky or Einstein. The Large Hadron Collider smashes particles at energies that recreate conditions a trillionth of a second after the Big Bang. Gravitational wave observatories detect space-time ripples from collisions billions of light-years away. Yet when it comes to dark matter and dark energy, these marvels might as well be stone tools. The problem isn't just technical, it's existential. If dark matter truly interacts only via gravity, and dark energy is an inherent property of empty space, how do you design an experiment to catch what leaves no fingerprints? History offers sobering parallels. Take the luminiferous ether, the presumed medium for light waves that 19th century physicists spent decades chasing. Its existence seemed obvious until Michelson and Morley's failed experiments paved the way for Einstein's relativity, proving the ether wasn't hidden, it was unnecessary. Could we be in a similar blind alley, constructing ever more elaborate detectors for something that requires not better instruments, but a revolution in thought? The philosopher of science Thomas Kuhn warned that paradigm shifts often come from outsiders precisely because insiders become too invested in existing frameworks. Right now, most dark matter searches assume particle-based solutions, but what if the answer lies in modified gravity, higher dimensions, or something beyond current mathematics? Then there's the cosmic clock to consider. Dark energy's accelerating expansion means that in 1 trillion years, all galaxies beyond our local group will have vanished over the observational horizon. Future civilizations will peer into a nearly empty void, their telescopes blind to the cosmic microwave background or the redshift patterns we use today. With no evidence of an expanding universe, they might reasonably conclude it's static and small. never suspecting they're inheriting fossilized knowledge from a privileged sliver of cosmic time. This chilling scenario, known as the Big Forget, hints that some truths aren't just hard to uncover, they're temporally forbidden, accessible only during brief windows in the universe's life. Yet perhaps the greatest lesson lies not in potential answers, but in the questions themselves. For all our frustration, dark matter and dark energy have gifted us something profound, a reminder that the universe owes us no clarity. The very particles that built our bodies and the stars we admire emerged from processes that didn't require our understanding to function. There's humility in that realization, a cosmic perspective that tempers our instinct to conquer mysteries with the wisdom to appreciate them. Whether these puzzles yield to future genius or persist as eternal enigmas, they've already reshaped our place in the cosmos, not as its masters, but as its students, forever catching fleeting glimpses of a syllabus written in shadows. From ghostly particles that slip through walls to an invisible force tearing space itself apart, these 30 mysteries reveal a universe far stranger than our ancestors ever imagined. We've chased dark matter through dwarf galaxies and colliding clusters, only to watch it dodge every detector. We've measured dark energy's grip on the cosmos, yet still can't say whether it's a constant whisper or a growing scream. The deeper we dig, the more the cosmos resists simple explanations, each answer peeling back another layer of questions. Think about what that means. Every telescope, every supercomputer simulation, every underground lab crammed with liquid xenon represents humanity's collective effort to shine light on shadows. And yet, after decades of searching, the best we can say is this: 95% of the universe is missing, and we have no idea where to find it. That's not failure, it's the most thrilling invitation science could offer, because the moment we stop being baffled is the moment we stop learning. Here's the wild part: you're witnessing this detective story in real time. Right now, telescopes like Euclid are mapping dark matter's fingerprints across billions of light years. Detectors buried under mountains are waiting for a single dark matter particle to whisper its existence. Theorists are sketching equations that might one day rewrite gravity itself. This isn't just history, it's a living, unfolding mystery, and every viewer hitting play is part of it. So what's your take? Maybe you're Team Wimp, betting on massive particles lurking in the dark. Or perhaps you're convinced axions are the key, those hypothetical wisps of quantum fluff. Maybe you think we've got gravity all wrong, or that the multiverse holds the answers. Drop your favorite theory in the comments, the crazier, the better. After all, the next big breakthrough might start with a wild idea someone dared to voice. One thing's certain, the universe isn't done surprising us. Hit subscribe to join the hunt as new clues emerge, because the greatest discoveries aren't behind us, they're hiding in the next data stream, the next flicker of light from the edge of the void. Stay curious, stay bold, and remember, the more we learn, the more wonderful the unknown becomes.